Hey, my name is Wissam Bijani and I'm going to be presenting our work on occlusion-aware manipulation. In this paper, we asked the question of how can a robot retrieve a desired object from the back of a shelf when this object is hidden behind other clutter objects, say a milk bottle in the back of a fridge or a shampoo on a supermarket shelf. Let's start by considering the following scenario. The robot is tasked with retrieving the oil bottle from the back of the shelf. The shelf height does not allow for the robot to look from the top to find and retrieve the oil bottle, nor do you assume access to a separate storage space where the robot could empty the shelf one item at a time until the oil bottle is found. The robot is then left with having to navigate its way through the clutter using prehensile and non-prehensile manipulation actions until the oil bottle is found, grasped, and retrieved from the shelf. The two main sources of uncertainty that makes this problem particularly challenging are the occlusion-based uncertainty and the physics-based uncertainty, and any solution that cannot handle these two sources of uncertainty simultaneously will have a hard time solving the problem. The occlusion-based uncertainty arises from the fact that the desired object might be just hidden behind the clutter objects, while the physics-based uncertainty arises when multiple objects are interacting, and this happens when the robot is navigating its way through the clutter. Objects will be pushing against one another, and these physical interactions are very hard to model, let alone plan over in a partially observable environment. Environments with partial observability are often modeled in literature as partially observable Markov decision process, or POMDP for short, where planning takes place over the belief space. State-of-the-art online POMDP planners, which are POMDP planners that runs in a closed loop, can handle large state space and reason over long action sequence in near real time. Unfortunately, they are best applicable in environments where we could define the action space at a high level of abstraction, say grasp object A or pick object B. Alternatively, model-free policies can control the robot in a low-level continuous action space, and by integrating memory units into their structure, say an LSTM layer into a neural network controlling the robot, they could even act in a partially observable environment. On the downside, however, they lack the ability to reason over long action sequences, particularly when physics is involved. In our previous work, we have proposed to combine model-free and model-based aspects to tackle environments with physics-based uncertainty. In short, at every action steps, we would map the state of the real world to a similar state in the physics simulator, and in the physics simulator, a look-ahead planner guided by a learned heuristic would perform a quick local search and send back to the real world the best action to execute. Our previous work, however, focused on fully observable environment. So in this paper, we extend this work to act in a partially observable environment. So the questions that we will be answering are where to place the hidden object in the simulator in order to perform the look-ahead search, and how to represent occlusions in the physics-based simulator, as well as how to train a heuristic to act on partial observations. The basic idea consists of interleaving real-world execution with an occlusion-aware look-ahead planner and simulation. So while running in a closed loop, the look-ahead planner will be evaluating several hypothesized states, each with its own prediction of where the desired object might be. Then, also in simulation, we'll be using a pre-trained neural network to guide a local search to evaluate those states before sending back the best action to execute on the real robot. I will now go over the details of this closed-loop execution scheme, then I'll briefly explain the training process of the neural network which made this whole thing possible. The first step in this control loop is to map the current observation from the real world to a similar observation in the simulator. To do so, we take the raw image from a gripper-mounted camera and process this image to detect the pose and type of the objects in the scene. Then, in the simulator, we will use color labeling to identify objects. So obstacles will be colored red, and the desired object, if detected in the observation, will be in green, while the robot will be colored blue, the shelf edge in black, and the shelf wall in brown. Most notably, we will also be coloring in gray the shaded areas behind the obstacles, and we do so by illuminating the scene from the point of view of the robot. Once we have reproduced the real-world observation in the physics simulator, the next step is to try to estimate where the desired object might be. By passing the image from the simulator through our pre-trained neural network, the generative head of the neural net will create a distribution over the likely locations of the desired object. This distribution, which you see here in green, is not only the result of the current observation, but also the result of the entire history of past observations, as our neural network has integrated memory unit into its structure. In this example, the predicted distribution has two peaks, That is, according to the neural network, these are the two most likely locations to find the hidden desired object. Hence, we create two root states. Each of those root states will have a desired object placed at its corresponding peak location. Although you still can't see the desired object because it just happened to be placed behind the obstacle, it's actually recreated there in the physics simulator and it will be treated by the physics engine to generate the physics interaction and the occlusions. The look-ahead planner will now explore each of those two root states independently. So let's have a look into how the look-ahead planner will explore root state 1. It works by running several stochastic rollout all from the same root state. It takes the current observation, passes it through the neural network, now acting as a heuristic, and sampling the policy head of the neural network for an action. This action is executed in the physics simulator, the robot advances and the reward is received. We also now have a new observation image. This process is repeated up to a predefined horizon depth, so in this case it is 3. We did not plan all the way to the goal, first because it is time consuming, second it's because over long action sequence the physics interaction in the simulator will not match the one in the real world. Instead, to estimate the return beyond the horizon, we use the observation image of the horizon state to query the value head of the neural network to get an estimate of the return beyond the horizon. So to recap, a stochastic rollout consists of following the policy few steps into the future, then querying the value function for an estimate of the return beyond the horizon. This process is repeated a couple of times, so here you could see two stochastic rollout, each of 3 steps deep. And then we compare the return between those two stochastic rollout. And we keep track of the first action of the rollout that yielded the highest return. Then, this highest return is scaled by the weight of its root state, where the weight of a root state corresponds to the height of its peak used earlier to place the desired object in the root state. So in other words, we're scaling the highest return by how likely it is to find the desired object at the predicted location. This whole process of a look-ahead search is then repeated over the other root states, so root state 2. We also get the return and scale it by the weight of its root state. Then the last step consists of picking the action that maximizes the return with respect to both the probability of the rollout and the probability of the location of the desired object. So let's recap now onto what we use the neural network for. First, we use this generative head to maintain a distribution over the location of the desired object. Second, we use this policy head to guide the stochastic search of the look-ahead planner. And third, we use the value head to estimate the return beyond the horizon states. Now the remaining question is, how was this three-headed neural network trained in the first place? Well, I should also note here that the nice thing about having the physics simulator integrated in the closed-loop execution scheme is that the neural network could solely be trained in simulation and does not require further training or adaptation in the real world. So back to the question of how was this neural network trained? We used the supervised learning technique to train the pose estimator of the neural network, and it was trained over ground truth data supplied to us by the physics simulator on the location of the desired object. We also used reinforcement learning, namely PPO, to train the value head and the policy head of the neural network. It proved to be quite challenging to train this neural network from scratch over the full task. Instead, we devised a learning curriculum to run the training process over. We started by easy tasks, where the shelf would have a low number of objects, so low clutter density, and we would also initialize the desired object further to the front of the shelf, so it's less likely to be hidden at the beginning of the task. Now, the better we get at solving the problem, the harder the problem gets. And by harder, I mean we would increase the clutter density and we would initialize the desired object further to the back of the shelf, hence increasing occlusion and the complexity of the physics. To validate our approach, we compared it against several state-of-the-art inspired baselines, among which is a model-based hierarchical planner, where at the high level, we use the set of predefined abstract actions that are executed by a set of handcrafted heuristics and another RT planner at the low level. We also looked at using model-free policies like the stochastic policy or the greedy policy, which acts directly on the output of the neural network, so no planning involved here. We also experimented with different parameterization of our approach, so different number of rollouts and different horizon depth. From now on, we will be referring to our approach as the hybrid approach, as it combines both aspects from the model-free and model-based techniques. Here's an extract from the simulation experiments. You can see here side by side the different approaches tackling the same problem. And you can also notice the noise being added on the physics and geometry parameters of the objects. The hierarchical planner is shown to waste a substantial amount of time replanning, as the low-level planners do not always produce the expected result by the high-level planner. The model-free policies, on the other hand, like the stochastic policy, can act in real time, and they're also reactive to the physics of the environment. But they also fail to master long-term reasoning over the physics. Our approach, on the other hand, balances between near real-time execution and long-term reasoning, while also being very robust against occlusion and physics-based uncertainty. We also tested our approach in a realistic 3D environment before actually running it on the real robot. Here you see the robot running in the Mujoko simulator, trying to find, reach, and retrieve the green object from the shelf. Planning is taking place in the Box2D physics simulator, where the neural network was originally trained. I'll now leave you enjoying these beautiful demonstrations of the hybrid approach controlling the real robot. Thank you.